Do I believe that climate change is real? Yes. And do I believe that climate change and global warming are likely to be largely caused by man's activities? Once again, yes. And do I believe that greenhouse gas emissions, carbon dioxide in the atmosphere, is the predominant cause of the observed warming? No, I don't. So what do I think is the primary cause of man-made climate change and global warming? I'd like to start with a NASA satellite image. This is a microwave satellite image of an area of Brazilian rainforest. The area inside the black line is an area where the forest has been cleared. This image shows the mean surface temperature at noon for August 2000. The area that has been cleared has a surface temperature 6 degrees Kelvin, which is 6 degrees Celsius, or 11 degrees Fahrenheit warmer than the surrounding forest area. So why is the cleared area warmer than the surrounding forest? I pondered over this for a while and eventually realized that it boils down to some basic physics. It boils down to the properties of water. More than 50% of a tree is water, and water has some unique physical properties. Firstly, water has a very high specific heat. The specific heat of a substance is the amount of energy or heat required to warm that substance up by a particular amount. The specific heat of water is 4.18 joules per gram per degree C. What this means is that 1 gram of water, which is 1 cubic centimetre, requires 4.18 joules of energy to warm it up by 1 degree Celsius. The specific heat of air, on the other hand, is 1 joule per gram per degree C. So water has a specific heat 4.18 times higher than that of air on a mass basis. If we now compare water and air on a volume basis, 1 cubic metre of water weighs 1,000 kilos and 1 cubic metre of air weighs 1.25 kilos. So water is 800 times more dense or heavier than air and has a specific heat 4.18 times higher than that of air. What this means is that a volume of water requires 3,344 times more energy to warm it up a certain amount as compared to an equivalent volume of air. Now 3,344 is a large number, and this demonstrates that air is relatively easy to warm up and water is exceedingly difficult. It also demonstrates the ability of water to absorb large amounts of solar radiation or heat for a minimal temperature rise. Water also has a very high latent heat of vaporization, 2,260 joules per gram. This is the energy required to change the state of water from liquid into a gas or vapor, so a large amount of energy is required to vaporize water. A forest or any vegetation is effectively a sponge or water blanket over the land surface. The forest is cooling the environment in two main ways. Firstly, by the high specific heat of water, the forest is absorbing large amounts of solar energy for a minimal temperature rise. Secondly, plants use the transpiration process. Transpiration is the process of water movement through a plant and its evaporation from aerial parts, especially from leaves. Through this evaporation process, plants are absorbing vast amounts of solar radiation or heat. What does one do on a hot day? You go to the beach or anything that involves water. A tree is effectively an evaporative air conditioner. Every tree and plant is cooling the environment, and every tree and piece of vegetation that we cut down is warming the planet. These physical properties of water explain why the area of uncleared forest is cooler than the cleared area. This is a table of temperature data. I have extracted these figures directly from the Bureau of Meteorology's website. I live in Melbourne, Australia, and have chosen a good cross-section of weather stations to Melbourne's southeast. These are all locations that I know having grown up here. The Bureau organises its temperature data into 30-year blocks. This is to iron out yearly variations and provide more consistent and meaningful figures. The table shows mean maximum and mean minimum temperatures for two 30-year blocks, 1951 to 1980 and 1981 to 2010, for each weather station providing 60 years of data. I have then averaged the mean maximum and mean minimum temperature differences for each weather station. Melbourne City shows a temperature rise of 0.65 of a degree Celsius over the 60-year period. Scoresby, which is an outer suburb of Melbourne, shows a temperature rise of 0.55 of a degree. Wonthaggi, which is a rural town 100 kilometres southeast of Melbourne, shows a temperature rise of 0.35 of a degree. Omeo is a near forest country town in the Great Dividing Range and shows a temperature increase of 0.15 of a degree. Tulangi is a forest location 70 kilometres northeast of Melbourne and shows a temperature increase of 0.05 of a degree. Cape Schanck is a coastal lighthouse overlooking Bass Strait and shows no temperature rise at all over the period. We have 90 years of data available for three of these stations. Melbourne City shows a temperature increase of 1.15 degrees Celsius over the 90-year period. Omeo, however, still shows a temperature increase of only 0.15 of a degree for the same period. I think the trend in this temperature data is completely obvious. The warming recorded at each site appears to be primarily a function of landscape modification. Bear in mind that landscape modification warming is not only local but is also regional and continental. Initially, the removal of vegetation is the first cause of warming. The erection of concrete structures and bitumen paving is a secondary cause of warming. Take note of Melbourne's overnight mean minimum temperature increase of 1.6 degrees Celsius over the 90-year period. This is more than double the daytime mean maximum temperature increase of 0.7 of a degree. This is due to city structures of concrete and bitumen, and I will explain why. This graphic shows the thermal properties of relevant materials. The energy figures show the relative amount of heat energy stored by each material. But the key number here is the low thermal conductivity of concrete. This number means that concrete or any similar rock material takes a long time during the day to warm up. Conversely, concrete takes a long time to dissipate that heat at night, tending to keep city environments much warmer through the night. I'm going to show you a segment now from an episode of ABC Catalyst. This segment focuses on a fall in winter rainfall across southern Australia.
But you'll see there's one part of Australia noticeably absent from this acute attack of fluid retention. It's my old stamping ground, the southwest of WA, which is where I am now, down amongst the karri trees. Well, underneath them actually, inside glorious Jewel Cave. Okay, so this is what I came here to show you. You see this black line? That's actually a water line, the high water mark from the late 60s. This was once a lake, up to here. But ever since then, the water has just drained away. The last of the water disappeared by the year 2000. And it's the same sad story across the region. The caves of Margaret River have lost their lakes and streams. Land use changes have compounded the problem, but this is a symptom of chronic dehydration.
So what we've got here is basically rainfall during April to November, and in the last 15 years in particular in the southeast of the continent here is about a 10 to 20% reduction in that rainfall.
That much, yeah.
That's right. And over here in the west we've seen the same thing, but that's actually occurred since about 1970. So they've had almost about 4 decades with much less winter rainfall than they used to have.
So why is southern Australia receiving less winter rainfall? It's because over decades we are observing a poleward shift in our weather systems. It's as though the whole weather map here in Australia is shifting further south. Southern Australia typically receives winter rainfall from Southern Ocean low pressure systems. You can see a large low in the centre of this winter weather map, with a cold front sweeping over southern Australia. The poleward shift of our weather systems means that the influence of these Southern Ocean lows and the winter rainfall that they bring is diminishing over southern Australia. Now, because Perth is further north than the southeast of the continent, this southwest tip of Australia was the first to experience this drop in winter rainfall in the 70s, followed 2 or 3 decades later by the southeast of the continent. We can see this poleward shift in weather systems very clearly in the Bureau of Meteorology's State of the Climate 2014 report. This image shows rainfall during the northern wet season, October to April, since 1996. As weather systems shift further south, the north of the continent is experiencing a greater influence of tropical moisture from the north, and the south of the continent is experiencing less rainfall from Southern Ocean lows and cold fronts that sweep over the south of the continent. The same rainfall pattern appears even more markedly during the Southern Hemisphere winter months from April to November, with large areas in the south now showing their lowest rainfall on record. There is another implication of this poleward shift in weather systems. If we compare Melbourne's temperature records with that of Sydney, 158 years of data show that Sydney's mean maximum temperature is 1.8 degrees Celsius higher than that of Melbourne. Melbourne and Sydney differ by only 4 degrees of latitude, so with a poleward shift in weather systems, we would expect to see some increase in average temperatures in a particular location. For years I puzzled over what could possibly be causing this poleward shift in weather systems, and then on one particular day a few years ago, the penny dropped. I recognised that high-pressure systems traversing the continent were now travelling at a lower latitude than they once did. Now, a high-pressure system is in fact dry air that is descending from the upper atmosphere. This air originates at the equator in an equatorial updraft driven by the sun's heat. After losing all of its moisture as it ascends in the atmosphere, this equatorial air then migrates north and south in the upper atmosphere, eventually sinking back down to Earth in a band of high-pressure cells about 30 degrees north and south of the equator. Some of this air then returns at ground level back to the equator, completing a loop of airflow known as a Hadley cell. I now recognise that the latitude of high-pressure cells must have something to do with what was happening at the equator. The research I then did showed that the equatorial low-pressure trough is in fact expanding or becoming wider. This widening of the low-pressure trough is in fact pushing weather systems poleward. And what could possibly be causing the expansion of the equatorial low-pressure trough? It's really quite obvious when you think about it. This image shows the line that marks the position of the Intertropical Convergence Zone, ITCZ, or Equatorial Low Pressure Trough, in both the Northern and Southern Hemisphere summers. We need to understand some intricacies of this map before we can go further. The first aspect to notice is the narrowness of the ITCZ over the Pacific Ocean. This narrowness is due to the fact that the ocean is made of water. Unlike over land masses, the sun is unable to create any hotspot on the surface of the ocean because of the fluid nature and enormous heat-absorbing capabilities of oceans deep, wide and vast, made of water. Notice now how the ITCZ extremities diverge significantly as we pass over the South American landmass. The two lines widen appreciably over the Amazon region. Looking further east, as we cross the Atlantic Ocean, the two lines converge again. They remain reasonably close together as we traverse tropical West Africa and then diverge again markedly as we cross the East African coast, which is drier and more sparsely vegetated. The ITCZ extremities remain quite wide over India and Southeast Asia and then converge quickly as they enter the Western Pacific. This widening of the ITCZ is a function of land masses and the thermal nature of the surface of those particular land masses. Deforestation in equatorial regions is changing the thermal nature of the land surface in these regions, resulting in a widening of the equatorial low-pressure trough. This in turn is pushing weather systems poleward. If we track high-pressure cells moving from west to east around the southern hemisphere, we can see that they follow a path on the same line as the ITCZ, but at a more southerly latitude. High-pressure cells typically sit high in the Indian Ocean, but as they approach the Western Australian coastline, they begin to deviate further south. By the time that a particular high-pressure cell reaches Eastern Australia, it is typically a few degrees of latitude further south. The same pattern can be seen in the Eastern Pacific, where high-pressure cells approach South America and are deflected significantly south as they pass under the South American landmass. Of particular climate change concern recently is the Antarctic Peninsula. The Antarctic Peninsula has shown a dramatic 2 to 3 degrees temperature increase over the last 30 years. At the same time, the Antarctic continent does not appear to be warming. If we look at the map, we can see that the Antarctic Peninsula is the northernmost point of the Antarctic continent and directly south of the Amazon region. I recently looked at a weather map and saw a high-pressure cell centered almost directly over the peninsula. It is quite unusual to see a high-pressure cell at 60 degrees latitude. It's no great surprise to me that the region is showing so much warming. Let's now have another look at the global temperature anomaly sequence from the last 40 years. If we focus on the Antarctic Peninsula, we can see a dramatic change occurring beginning in about 1980. We can see an area of warming appear over the peninsula. We can also see a distinct corresponding area of cooling to the west. What is noteworthy is that the area of warming has a distinct horseshoe or semicircular shape to its southern extremity. This shape, in my observation, is the telltale sign of high-pressure cells tracking further south than they once did as they pass under the South American landmass. It appears that this tongue of warmer air is displacing cold polar air over the Antarctic ice sheet and squeezing it north into the region to the west. This graphic shows 30 years of satellite temperature data. What is interesting to note is that the southern hemisphere shows no significant warming. At the same time, the northern hemisphere shows more than half a degree of warming. How do we account for this? If we draw a line through our map marking the equator, we can see that the greatest percentage of landmass on Earth is in the northern hemisphere. The same would apply to population. The southern hemisphere is predominantly ocean. From this data, it appears that the warming observed in each hemisphere is a function of landmass. Let's return now to the temperature anomaly sequence. We can clearly see that the bulk of the warming is in the northern hemisphere. This pattern of warming agrees with the satellite data. It almost certainly appears to be related to land masses. The bulk of the warming is also towards the poles. This directly contradicts the pattern of warming expected if greenhouse gases are responsible for this observed warming. With greenhouse gas warming, we expect to see a warming in the middle of the troposphere over the equator.
John Hemaker points out that the greenhouse effect has to occur most strongly in the tropics, since that is the area which already gets the most sunlight. The poles in higher latitudes, which get relatively few of the sun's rays, they're even dark much of the year, should be warmed very little by a greenhouse effect. When the tropics heat up and the poles don't change much, the temperature difference between these two areas of the globe increases.
My current explanation for the warming that we are observing in the temperature anomaly sequence is that there are two main factors. Firstly, the poleward shift in weather systems is bringing each location a warmer climate zone. Secondly, if we look at global circulation, the equator is hot and the poles are cold. Global winds are primarily driven by this temperature differential. In short, winds blow from the equator to the poles and back again. And as winds travel from equator to pole over the surface of the Earth, they are being warmed on their journey and accumulating heat as they progress. If vegetation has been removed over this segment of the journey, winds will approach the pole warmer than they once did. Where once they blew through cool forests, today they blow over a different landscape, hotter, with less vegetation and accelerated by desertification. In short, we are blasting hot air to the poles. Every initiative or activity of mankind is undermining the planet's basic mechanism to keep itself cool.